Now we are going to present our word transparent load balancing of MPI programs using OmpSs-2 clusters and DLB. Our main motivation to do this work is that loading balance is a very important source of inefficiency in HPC. The issue is only getting worse because the application and the system complexities are increasing with time, and load balance implementation is generally time consuming and obscures the application logic. It also may need extensive code refactoring and may not be feasible in very dynamic codes. Global partitioning gets harder as the size of the cluster continues increasing with time too. The main contributions in this paper are: first, the extension of the OmpSs-2 cluster programming model to provide interoperability with MPI for load balance purposes. We provide mechanisms for fine-grained and coarse-grained balance using LEWI and DROM, and we provide two methods for core allocation algorithm, one using local convergence and the other using a global linear program formulation. We have also a way to limit the amount of communication and state by using an expander graph. OmpSs is a directives task-based programming model developed by BSc for research purposes. OmpSs-2 is the second generation of the programming model developed to support more fine-grained tasks and other optimizations. OmpSs-2 cluster is a task offloading extension of OmpSs-2. Any valid OmpSs-2 program with complete dependencies annotations is a valid OmpSs-2 cluster program. The parallelism OmpSs is expressed using code directives. The original code is compiled by a source-to-source compiler called Mercurium, and then the new code is compiled by a native compiler. The native compiler makes calls to the Nano6 API and generate tasks. You can see from the image on the left how a normal application should execute in OmpSs cluster. The application, the main, creates some tasks using the directives, and then OmpSs cluster decides to offload part of these tasks. The offloaded task can also generate more tasks, and there is not any limitation in the offloading or the nesting levels. From the image on the right, we can see more or less how the runtime works. The initial application, that is the main, is executed by node 0. Then the application makes Nano6 calls, and then the underlying MPI takes care of tasks offloading, communications, and data transfers. All this happens in a completely transparent way for the final user. DLB defines itself as a library devoted to speed up every applications and maximize the utilization of computational resources. DLB is intended to provide load balancing inside the node by redistributing or reassigning resources to one, two, or multiple applications running in the same node. It provides a straightforward API to enable dynamic load balancing among multiple processes and is compatible with MPI, OpenMP, and OmpSs. Since version 3.0, DLB is divided in modules. We have the LEWI, which is the language idle module. We will explain in detail later. We have the DROM, and there is another module called TALP, which track applications like performance. In this work, we use two of the three modules of DLB, LEWI and DROM. They work different because LEWI blend the cores when they are not used by the main application in a more fine-grained way, while DROM changes the ownership, the semi-permanent ownership of the cores. In this example, you have an application where you have two applications, A and B, that are running on the same host in the same node. But the application A is not using all the resources or its resources, and the application B is high loaded. In this case, you have one core that is idle, and LEWI in this case will lend the core temporarily to application B to do part of the work, but it can claim the resource, the extra core, back at any moment. On the other hand, the DROM, what will do is transfer the semi-permanent ownership of the core to the process B, and then it is not possible to claim it back unless the application B gets low loaded and can let the application can transfer the ownership to application A again. Our proposal is a way to rebalance hybrid MPI plus OmpSs applications. Normal MPI applications have worked in single program multiple data way, which is what we see in this dimension, but we propose to add helpers in the other nodes. Every app rank in one node, in this case app rank in node 0, has a helper in node 1 and node 2. In this dimension, OmpSs cluster take care of redistributing the data, and in this dimension, DLB take care of redistributing the resources. Here we show how load rebalance works with a normal DLB application when using MPI. We have 16 ranks on a node, so we have 2 processes per node. When one of the app ranks gets high loaded and the one sharing node with it is low loaded, then DLB comes in actions to rebalance the work by transferring some of the resources in the rank 9 to the rank 8 and rebalancing the work. The approach is in general very effective, but is constrained within the node. When the imbalance is among different nodes, this is not enough to solve the imbalance problem. In this case, the offload degree is 1, which means that the app ranks do not send word to any helper in a remote node. The opposite situation is when we have helpers in all the other nodes. In this case, we can solve completely the imbalance problem because any application is able to send word to any other application, to any other node. But the problem is that the number of communications increase by a factor of n squared, which in general can be worse than the imbalance problem itself. In this work, we address these problems proposing a solution in between. We construct a bipartite graph where we can control the offload degree. We can see in the picture that when the degree is 2, then every app rank has one helper in a remote node. It will be able to offload word to that helper in some conditions. If we increase the degree, for example, to 3, then every app rank will have 2 helpers in 2 different nodes to offload word to. If we go to the same example that we saw before, then if the app rank gets high loaded, then there is not only one place to look resources for, that before was the rank 9. Now we have 2 helpers that DLB can use to check if some of the ranks in the same nodes are low loaded, and it can transfer resources to the helper in order to execute part of the work that originally was executed by rank 8. In this case, in the horizontal axis, then DLB will redistribute the resources, while in the vertical axis, OmpSs cluster will redistribute the work. When using the DROM, the ownership of course is updated dynamically as the execution progresses. We propose 2 different approaches to do that. The first and simpler one is the local convergence. Basically, it balances the load per core among workers on the same node, but the workers on a node coordinate to ensure that the number of cores by worker is proportional to its busy cover average. This is simpler to implement and understand, but as a drawback, it doesn't minimize the amount of task offloads or communications. We can see here on the right that even after the application gets balanced, it still gets offloading work between the 2 nodes, even when it is not necessary. The global solver, on the other hand, employs an external application to do the distribution. It uses the average like in the previous approach, but the work is summed across all the workers in the app rank. There is an heuristic in the application to minimize the offloading only it is necessary, and it always finds a solution to balance the load. We can see here in the example on the right that after, when the time progresses, then the application gets balanced, but without offloading work unnecessarily. In our methodology, we compute the imbalance by dividing the maximum load by the average load for every app rank. A value of 1 means that the application is perfectly loaded, and for example a value of 2 means that the critical path has roughly twice the length than with perfect load. For benchmark, we use essentially two applications. The first is Alya MicroPP, which is an Alya plugin for 3D final elements library for microscale solid mechanism in composite materials. The unbalanced execution in this case comes because some of the elements can become nonlinear and require much more calculation than the linear ones. On the other hand, we have the n-body application, which is a parallel implementation of the Barnett-Hunt using orthogonal recursive bisection. This application is well balanced from the beginning, but in our benchmark, essentially what we did was to run it in a different machine, in this case node 3, and make one of the nodes slower than the others. Most benchmarks were performed in 64 nodes in the general purpose partition of Marennostrum 4, where every node has two 24-core Intel Xeon Platinum 8160 at 2.10 GHz, 96 GB of physical memory and 32 MB of L3 cache. For the network, we have 100 GB per second inter-omnipath. For different speed imbalance tests, we use node 3, where every node has two 8-core Intel Sandy Bridge E5 2670, where the normal nodes had 3 GHz of speed and the slow ones were set to 1.8 GHz. This slide shows a trace of Alya MicroPP in 4 nodes with a graph degree of 2. The original version had an imbalance of 2, and we can see that when not using DLB, in this case node 0 is most of the time busy because it's very high loaded, while the other nodes has almost no work. They spend most of the time doing nothing. On the right we show the ownership of the cores, and we see that the ownership doesn't change with time. Every node is and every application has the ownership of its own cores. When using Lewy, on the other hand, we can see that how part of the work that initially was executed in node 0 is now executed in node 1. Lewy allows to transfer part of the works, to execute part of the work in node 0, but without transferring the ownership of the core in a semi-permanent way, and as we can see on the image on the right. Using Lewy reduced the execution time to 85% of the original time, and the imbalance that used to be 2.0 is now 1.33. Finally, when using DROM, we can see how node 1 after some time start executing more and more work from up rank 0 up to a point that most of the work that it is executing is basically from the up rank 0. The work that originally was in node 1 from up rank 1 migrates to node 2, but also the ownership, as we can see here on the right, has changed. This is the reason why we don't see these lines of up rank 1 executing anymore in node 1 after some time. The DROM reduced the execution time to the 65% of the original time, and the imbalance from 2 to 1.15. This graph shows the execution time for an Alya MicroPP application on Marennostrum 4 with the number of nodes and the graph degree. We can see here that when we increase the degree of the graph, in general the times tend to get lower. But then if the degree is too high, which happens here especially on the right, we see how the number of communications grows and then the times get worse than the original application. The n-body benchmark or node 3 with one slow nodes, we can see that it provides similar results on 16 nodes. 20% of improvement respect to the baseline with a graph degree of 3. From the two applications, the conclusion is that the global core allocation achieved excellent resource improvement in load balance with an offload degree of 4. In conclusion, this paper introduces an automatic and transparent load balancing mechanism for MPI plus OmpSs-2 programs, keeping the programming model simple and that requires a small change in existing applications. Our method uses OmpSs-2 cluster to offload tasks to other nodes and DLB as the underlying mechanism to allocate resources. We leverage the DROM module of DLB to reserve core on other nodes and thereby address coarse-grained load imbalance, and we use LEWI to react to fine-grained imbalance. Our system uses a sparse expanded graph to minimize the amount of point-to-point communications and state, and we show a 46% reduction in time for MicroPP and 20% for MBody on 16 nodes when one node is slow. We perform a sensitive analysis of imbalance and obtain results within 10% of perfect load balancing for an initial imbalance of up to 2.0 on 8 nodes. Our software is released as open source with the hope that our work can be expanded and adopted in practice.